Imagine for a moment that the universe pressed pause on everything you see. What if the space around you, the air you breathe, and the light entering your eyes all hid secrets that only reveal themselves when the ordinary rules of reality loosen their grip? What if a single particle could whisper two truths at the same time, choosing two paths without choosing, living in a place where decision itself has no meaning? And what if the smallest pieces of nature do not behave like tiny stones or tiny sparks, but like something far stranger, something that refuses to stay in only one state or one location? These questions seem impossible, yet the earliest clues that reality might not be what it appears came long before scientists even knew what they were looking at. The mystery begins not with advanced machines or futuristic laboratories, but with glowing metal, warm light, and a nagging problem that refused to go away. At the end of the 19th century, physics appeared complete. The great equations of electricity and magnetism were united by the work of James Clerk Maxwell. The laws of motion had stood strong since the era of Isaac Newton. Every force known to science seemed to follow predictable rules. And yet, there was a quiet puzzle hiding inside something as ordinary as a heated object. When metal is heated, it glows first a dim red, then a bright orange, then nearly white. This glow is called black body radiation. And for many years, physicists tried to describe it with the mathematics they trusted, but each attempt failed. The predictions of classical physics claimed that as the light shifted toward shorter wavelengths, the energy emitted should rise without limit. This was impossible, and experiments showed a clear curve that peaked and then dropped. Nature did not match the theory. It was in this tension between prediction and reality that the first crack in the classical world appeared. In the year 1900, Max Planck stepped forward with a desperate idea. He suggested that energy did not flow in a smooth and continuous stream. Instead, it came in tiny packets. He did not know why. He did not claim to understand what these packets meant. He simply saw that the mathematics required this strange step. By treating energy as a series of discrete jumps, he reproduced the exact curve of black body radiation. The curve matched perfectly, and yet it made no sense within the worldview of the time. Planck had opened the first door into the quantum world, although he had not yet realized what would pass through it. 5 years later, Albert Einstein pushed the idea even further. In studying the photoelectric effect, where light strikes metal and ejects electrons, he discovered that classical physics could not explain why the electrons behaved as they did. According to the old rules, a brighter light should always eject more energetic electrons. But experiments showed something different. Only light of certain colors, which meant certain energies, could free electrons at all, even if the light was dim. Einstein proposed that light itself was made of the same kind of energy packets Planck had used. He called them light quanta, what we now call photons. With that single step, he transformed light from a smooth wave into something deeper. Light behaved like both a wave and a stream of particles. This was the beginning of wave-particle duality, a concept that would eventually point directly to the idea of superposition. The mystery deepened in the year 1924 when Louis de Broglie suggested that if light could act like both wave and particle, perhaps all matter did the same. Every electron, every proton, every atom might have a wave associated with it. It was a bold and almost unsettling proposal. Nothing in daily life hinted that a stone or a grain of dust or even a tiny electron carried a wave that determined where it might appear. Yet, when de Broglie wrote down the mathematics, the idea was elegant, simple, and startling. If matter had waves, then the smallest particles could interfere in the same way that ripples on a pond interact. They could overlap, reinforce, or cancel each other. And from this idea, the stage was set for the greatest and most troubling discovery of all. In 1927, the Davison-Germer experiment confirmed the wave nature of electrons with undeniable clarity. When a beam of electrons struck a crystalline nickel target, the scattered electrons formed a diffraction pattern, the same kind of pattern produced by waves of water or light. Matter behaved like a wave, but at the same time, each electron arrived like a particle, appearing at a single point on the detector. The experiment was repeated, refined, and verified. The result was always the same. Electrons were not simply particles or waves. They were something that did not fit either category. They belonged to a new domain of physics, one in which the rules of the ordinary world did not hold. The birth of quantum weirdness did not come from speculation or imagination. It came from hard evidence, from stubborn experiments that refused to obey classical expectations. Every step forward forced scientists to abandon another comfortable assumption about reality. Energy is not a continuous flow. Light is not purely a wave. Matter is not purely a particle. The universe, it seemed, allowed nature to exist in multiple overlapping states at once. The seeds of superposition were already planted, and the strange new landscape of quantum mechanics waited just beyond the horizon, ready to reveal that the fabric of reality was far more fluid and mysterious than anyone had ever guessed. The deeper scientists looked into the early experiments, the more unsettling the picture became. The idea that matter behaved like a wave was not just a mathematical trick or an abstract interpretation. It was something the universe insisted on every time an experiment was performed carefully enough. But this raised a question that no one at the time could answer. If an electron behaved like a wave, then what exactly was waving? Nothing in the classical world resembled such a thing. Water waves needed water. Sound waves needed air. Even light waves, once thought to require an invisible medium, were known by then to be oscillations in electromagnetic fields. But the wave of a particle seemed not to be a wave in any substance at all. It was a wave of probability, a wave that governed where a particle might appear, yet not tied to any material form. It was as if the universe carried its own hidden blueprint inside every particle, a blueprint that only became visible when measured in the right way. Physicists struggled to make sense of this. The electron in the Davison-Germer experiment created a diffraction pattern only when many electrons were fired, one after another. But even when the electrons came through the apparatus one at a time, separated so that no two could influence each other, the pattern slowly built up. A single electron behaved like a single dot on a screen, yet over time the dots collectively formed the kind of pattern that only waves produce. How could each electron know where the others had landed? How could it participate in a collective wave structure when it was traveling alone? The only explanation left was that each electron carried its own internal wave, a wave that spread out, interfered with itself, and guided the electron to land in places determined by that interference. This was not a metaphor, it was a description forced by experiment. The world did not behave like the solid and predictable place people assumed it was. Instead, particles behaved as if they existed in many overlapping possibilities, some of which reinforced and some of which cancelled each other. These possibilities existed simultaneously, not as guesses but as real physical states. Only when a particle was observed did it reveal a definite outcome. Before that, it behaved in ways that could only be described through waves of probability. The concept was uncomfortable, but the evidence left no room for denial. By the late 1920s, the scientific community was rapidly shifting from a classical worldview to one in which probability, uncertainty, and overlapping states ruled the domain of the small. The classical picture of particles moving along definite paths had been replaced by a world in which paths themselves dissolved into clouds of possibility. When Einstein and others questioned whether these ideas represented a complete understanding of nature, the experiments continued to reinforce the strange new picture. Every test, every measurement, every new phenomenon aligned with the quantum view. The universe was not merely complicated, it was fundamentally different from the expectations built over centuries of classical thought. It was at this point that Erwin Schrödinger introduced his equation, a mathematical description that allowed physicists to calculate how these probability waves evolved. He did not know at first that the equation he wrote down would become the central pillar of quantum theory. He only sought to find a model that explained de Broglie waves, but his equation worked brilliantly, predicting patterns in atoms, energies of electrons, and the structure of matter itself. It suggested that electrons did not orbit the nucleus like planets around the lowercase sun. Instead, they existed in standing wave patterns, spread out through space, occupying regions defined not by orbits, but by probabilities. The quantum world was less a mechanical clock and more a shifting tapestry woven from waves of possibility. Yet even with these breakthroughs, the experiments from this period had already planted the most profound seed of all. If particles behaved like waves, then they could exist in superpositions of states. They could be here and there, moving and not moving, in multiple possible configurations at once. The evidence pointed toward this long before the word superposition became a central idea. Every diffraction pattern, every interference curve, every unexplained experimental detail whispered the same message. The world, at its smallest scale, is built from layers of possibility stacked on top of each other. Only when we measure do we peel back one layer and reveal a single result. The birth of quantum weirdness was not a moment of philosophical insight, but a chain of stubborn puzzles that refused to fit inside the classical world. Scientists kept following the clues, not because they wanted a strange universe, but because the evidence demanded it. Each new discovery added another piece to a picture that defied every expectation. And as the 20th century moved forward, it became clear that these early experiments were not isolated oddities. They were the first signs of a deeper truth, a truth that would soon be revealed with even more startling clarity in the experiment that defined the quantum world more than any other. The more the early quantum pioneers pushed forward, the more they realized they were standing on the edge of a completely new understanding of nature. What began as small cracks in classical physics were widening into a vast canyon, revealing a landscape that did not resemble anything familiar. The idea that a particle might carry a wave of probability was already unsettling, but the questions uncoiled one after another in ways that no one expected. If the electron behaved like a wave, then did it choose a path? Or did it travel all available paths at once? If light behaved as both a wave and a particle, then what decided when it would manifest as one or the other? These questions had no classical answers, and they were not philosophical games. They came directly from experiments that had been repeated and confirmed across laboratories around the world. Within this growing mystery, another realization began to take shape. The universe did not speak in the simple language of visible objects and predictable motions. Instead, it seemed to whisper in waves and probabilities, with each experiment acting like an interpreter, translating a strange dialect of nature. Even something as basic as the position of an electron became a question not of where it was, but of where it could be. Its existence was smeared across space, not as a physical blur, but as a set of simultaneous possibilities. This was not due to measurement limitations or human ignorance. It was built into the structure of reality itself. As researchers dug deeper, they found that atoms, once imagined as miniature solar systems, were nothing like the tidy models drawn in textbooks. Electrons did not circle the nucleus like planets around the lowercase sun. Instead, they formed clouds of probability shaped by the mathematics of the Schrödinger equation. The idea that matter could exist in overlapping configurations was no longer a speculative thought. It was a requirement for explaining how atoms held their shapes and how the periodic table emerged from the patterns of quantum waves. Without these superpositions, the world as we know it would collapse into a formless mess. Every chemical bond and every physical property depended on the delicate interference of probability waves inside atoms. This realization brought a powerful shift in the way scientists thought about nature. Classical physics had always focused on certainty. If the initial conditions of a system were known, then its future could be predicted exactly. Quantum mechanics shattered that view. Even with perfect information, one could not predict where a single particle would land, only the likelihood of its landing in one region or another. The universe had replaced certainty with probability, but not in a chaotic or random way. the probabilities followed strict mathematical rules, rules that could be calculated with incredible precision. Nature was not careless. It was simply structured differently than expected. But behind every new insight, there lingered a profound and unsettling question. If particles behaved like waves, and if waves represented overlapping possibilities, then what happened when someone tried to observe the system? Why did the particles suddenly appear in one definite place? What rule governed the shift from possibility to reality? Early physicists struggled with this, and the tension became part of the growing narrative of quantum strangeness. Some thought the wave was real. Others believed it was only a tool for predictions. Yet no matter how they debated, the experiments kept pointing to the same conclusion. Before measurement, a particle did not occupy a single definite state. It existed in a blend of possibilities, a superposition of outcomes that only resolved when measured. This strange duality formed the heart of the quantum revolution. The familiar rules of classical motion had been replaced by a world where existence itself seemed fluid. The old laws were not wrong, but they were incomplete. They described the large-scale world, the world of everyday experience, where superpositions vanish almost instantly. But in the tiny realm of electrons and photons, those old rules could not reach. The quantum world demanded a new language, a new logic, and a new way of thinking about nature. As the first chapter of this discovery came to a close, the evidence stood like a lighthouse pointing toward the strange territory ahead. Light behaved as both particle and wave. Matter exhibited interference patterns that only waves could produce. Energy came in discrete packets, not continuous flows, and probability waves guided the behavior of particles before any measurement was made. Each discovery added another layer to a picture that was as mysterious as it was undeniable. All these clues converged on a single, now inescapable conclusion. If matter behaved like waves, and if these waves represented overlapping possibilities, then the universe allowed particles to exist in multiple states at once. This was the birth of superposition, not as a philosophical guess, but as an experimental necessity. And nothing revealed this truth more clearly, more elegantly, or more powerfully than the experiment that would soon dominate the story of quantum mechanics. It was an experiment so simple that it could be drawn in a few strokes, yet so deep that it forced the scientific world to confront the true nature of reality. Everything that began with glowing metal, scattered electrons, and desperate attempts to fix mismatched equations was leading toward it. The next step in this journey would uncover the core of quantum behavior, the place where all the strange pieces finally aligned. And as we step forward into that experiment, the question that once hovered in the background now moves to the front. If matter behaves like waves, what exactly is waving? There are moments in the history of science when a simple question unravels an entire understanding of the world. The double slit experiment is one of those moments, a quiet doorway into a realm where nature behaves in ways that seem almost impossible. It does not require giant machines or complex instruments. It can be drawn with 2 lines on a page. Yet hidden within that simplicity is the most direct revelation of superposition ever discovered. It shows not only that matter behaves like waves, but that a single particle can explore multiple possibilities at once, leaving behind a pattern that no classical idea can explain. And it all begins with an experiment performed long before the quantum world had a name. In the early 19th century, Thomas Young set out to measure the nature of light. At that time, many scientists believed light consisted of tiny particles. Others argued that it behaved as a wave. Young decided to test which view aligned with reality, and he did so by shining light onto a barrier with 2 narrow slits cut into it. When the light passed through the slits, it struck a screen on the other side. If light were made of particles, then each particle would travel through one slit or the other, forming 2 bright regions on the screen. Instead, Young observed a series of bright and dark stripes, the exact pattern expected from waves interfering with each other. Where the peaks of one wave lined up with the peaks of the other, the light intensified. Where the peaks of one wave met the troughs of the other, the light diminished. This interference pattern became the signature of wave behavior, etched into the screen like a message written in alternating bands of brightness. For decades, this result stood as strong evidence that light was a wave. But as the 20th century approached, new discoveries complicated the picture. The photoelectric effect showed that light also behaved like discrete packets of energy. If light was made of tiny quanta, how could it still produce a wave pattern? The question lingered until scientists began to apply the double slit idea, not just to light, which already seemed ambiguous, but to matter itself. If Louis de Broglie was correct, then electrons should behave as waves and should therefore form an interference pattern. This was not a metaphor or a philosophical claim. It was a testable prediction. If electrons possessed wave properties, then the double slit experiment would reveal it instantly. The experiment was finally performed in the year 1961 by Klaus Jonsson. When electrons were fired toward the double slit barrier, the result was astonishing but undeniable. The electrons formed the same interference pattern that light once had. Yet each electron still arrived as a single dot on the detection screen, a tiny particle landing at a single point. Somehow the individual arrivals built up a pattern that only waves could produce. It was not that the electrons influenced each other, because they could be fired one at a time, with long intervals between them. The interference still emerged. It was not that the electrons traveled through one slit or the other in a hidden way, because any attempt to measure which slit an electron passed through destroyed the pattern entirely. Nature behaved as if each electron took both slits at once, interfering with itself before appearing as a localized impact. This strange behavior did not remain limited to electrons. Over the decades, physicists repeated the double slit experiment with neutrons, atoms, and even complex molecules. In 1999, a team in Vienna performed the experiment with fullerene molecules containing 60 or 70 carbon atoms. These molecules were far larger than any quantum object previously tested, yet they also produced an interference pattern. They behaved like waves even though each molecule was a cluster of dozens of atoms, each atom containing protons, neutrons, and electrons. The fact that such a large and complex object could pass through two slits simultaneously and interfere with itself was a clear message. Superposition was not limited to light or to the smallest particles. It was built into the structure of the universe itself. The most striking version of the experiment came when physicists decided to make the particle arrivals visible one by one. They set up detectors capable of recording the exact position where each particle struck the screen. At first, the pattern seemed random, a scattered collection of dots with no clear structure. But as more and more particles arrived, the interference pattern began to form, first faintly, then unmistakably. Even though each particle arrived alone, even though there was no crowd of particles to push or pull each other, the final image matched the exact shape predicted by wave interference. It was as if each particle explored multiple paths, combined them, and then materialized in one location determined by the interference of those possibilities. Every classical intuition fails here. A marble cannot roll through two openings at once. A raindrop cannot split itself and interfere with its own motion. But particles in the quantum world are not marbles or raindrops. They do not choose a single path. They exist in superpositions of paths until something forces them into a definite outcome. This is not an abstract idea. It is a direct conclusion drawn from experiment after experiment. The double slit experiment is not merely a curious demonstration. It is the cornerstone of quantum mechanics because it reveals superposition in the most unfiltered form. It shows that particles behave exactly as if their wave functions guide them through multiple possibilities simultaneously. The mystery becomes even deeper when one attempts to measure which path the particle took. When detectors are placed near the slits to determine which slit the particle passes through, the interference pattern vanishes. The particles now form two clusters, one behind each slit. just as classical intuition would expect. The wave-like behavior disappears entirely, yet the only change is the introduction of path information. Nothing pushes the particles into new trajectories. Nothing alters the apparatus in a mechanical sense. The act of measurement removes the ability of the particle to remain in a superposition of paths. It collapses the overlapping possibilities into a single choice. This shows that superposition is fragile, easily destroyed by information being leaked into the environment. Every version of the double-slit experiment, from the simplest to the most advanced, tells the same story. Particles possess wave-like properties. They exist in multiple possible states at once, and the world we observe, the solid and familiar world, appears only when the act of observation forces these possibilities into a single outcome. The experiment is a window into the true nature of reality, revealing that the universe operates on rules far stranger and far richer than anything imagined during the classical era. As we move forward, the next step is to understand the mathematics behind this behavior, the wave function that governs these events and describes how superposition unfolds. The deeper scientists studied the double-slit experiment, the more they realized that it was not only a demonstration of wave-like behavior, but also a direct confrontation with the limits of classical thinking. In the classical world, every object travels along a definite path. If a pebble is thrown, it moves through a single trajectory. If water flows through two channels, the molecules do not transform into something new. They simply divide and then rejoin. But in the quantum world, particles do not choose a single route. The electron approaching two slits does not decide left or right. Instead, it behaves as though it passes through both slits simultaneously, exploring all available paths until it reaches the detection screen. This idea feels impossible, yet the pattern on the screen leaves no room for doubt. The interference arises only if the possible paths remain intact and unmeasured. Consider a single electron leaving the source and heading toward the barrier. If the electron were a classical object, it would pick one slit and travel through it. But the pattern it creates when repeated many times is not the predictable pair of bright regions expected from such behavior. Instead, the electrons land in regions where they should not cluster if only classical laws applied. They gather in bands where wave peaks reinforce each other and avoid regions where wave peaks cancel with wave troughs. The only way to produce this pattern is for the electron to act like a wave, with part of its wave passing through one slit and part through the other. The wave then recombines on the far side of the barrier, creating a pattern of reinforcement and cancellation. But when the electron finally lands, it is always detected as a single point, never split into pieces. It behaves as if it spreads out like a wave, but arrives like a particle. This dual nature puzzled the early quantum pioneers and continues to challenge intuition even today. Yet every version of the experiment repeats the same message. The interference pattern exists only when the electron remains unaware of which path it has taken. The moment any device tries to determine whether the electron passed through the left slit or the right slit, the interference vanishes. The bands dissolve into two clusters. The electron behaves as if it took only one path, even though moments before it acted like a wave exploring both. This shift is not caused by the physical bump of a detector or the pressure of measurement. It happens merely because information about the path becomes available. The universe seems to treat information itself as a physical quantity, capable of altering the behavior of particles. This is one of the most remarkable lessons of the double-slit experiment. The world does not merely exist independently waiting to be observed. The structure of possibilities changes when information is gained, even if that information is subtle or indirect. When the path is unknown, the electron remains in a superposition of states. When the path is known, even if no one looks at the data, the superposition ends. The interference disappears because the particle cannot remain in overlapping states when the environment holds clues about its journey. This dramatic shift illustrates the fragility of quantum superposition and foreshadows the ideas of decoherence that would emerge decades later. Scientists pushed this concept even further by designing variations of the double slit experiment in which the path information could be erased after the particle passed through the slits. These quantum eraser experiments showed that the interference pattern could be restored if the path information was removed. This does not mean that time is being altered or that the particle is changing its past behavior. Instead, it confirms that interference requires the absence of distinguishable path information. When that information is erased, the universe once again allows the wave-like superposition to unfold, and the pattern reappears. Another extraordinary development occurred when researchers conducted the experiment with increasingly massive objects. The heavier the particle, the more classical its behavior was expected to be. Yet the experiments continued to produce interference. Atoms interfered. Molecules interfered. Clusters of dozens and even hundreds of atoms interfered. In more recent experiments, molecules containing thousands of atoms, complex shapes, and significant internal structure still produced interference fringes when sent through carefully prepared slits. These molecules were not abstract mathematical entities. They were large enough that their vibrations, rotations, and interactions had to be controlled with extraordinary precision. Yet when these systems were isolated well enough from their environment, their wave-like nature revealed itself just as clearly as it had for electrons and photons. This expansion of the double slit experiment into the domain of larger and larger objects demonstrated a fundamental truth. Quantum behavior is not limited to the smallest scales. It is not restricted to photons, electrons, or atoms. It is a universal feature of the physical world, present in everything but usually hidden by interactions with the environment. In principle, even objects visible to the naked eye could display quantum interference, but in practice, they interact with their surroundings too strongly and lose their superpositions before any pattern can form. The double slit experiment also provided the first glimpse into how measurement interacts with quantum systems. When a particle is measured, the superpositions disappear. But when it is left alone, the particle behaves as if it is many possibilities at once. This relationship between knowledge and outcome is at the heart of quantum mechanics. It does not imply that consciousness or human observation plays a special role. Instead, it shows that any interaction capable of extracting information from the system, even unintentionally, can break the coherence of the wave function. By the time the scientific community fully absorbed the implications of this experiment, it was clear that the double slit was not simply an interesting curiosity. It was a direct doorway into the structure of the quantum world, forcing scientists to rethink the nature of motion, information, and reality itself. The experiment connected the wave-like behavior of matter with the probability-based predictions of quantum mechanics, showing that the mathematics to describe this behavior must reflect the existence of superpositions. And so the next step in this journey leads directly to the wave function, the mathematical object that holds the key to understanding how these overlapping possibilities evolve. As researchers refined their understanding of the double slit experiment, they began to appreciate the depth of its implications. It was not simply an experiment that revealed something curious about particles. It was a direct expression of a principle woven into the heart of quantum mechanics. The pattern on the screen was not a decorative curiosity, but a map of probability, shaped by the invisible wave that guided each particle. The more scientists examined this pattern, the more they understood that it was the purest demonstration of superposition. A particle did not choose a path until a measurement forced it to. Instead, it followed all paths in a delicate combination that only revealed its structure when many particles accumulated on a screen. This way of thinking required a shift from the traditional view of the world. In the classical picture, reality existed independently of any observation. A stone had a single position, a single path, a single history. But in the quantum world, reality unfolded as a blend of possibilities, each one layered on top of the others until the act of measurement locked the system into a single outcome. The double slit experiment showed this clearly. When the electron had no knowledge of which slit it passed through, it behaved like a wave, forming a pattern that required both paths. But when the path information became available, even without anyone looking at it, the wave-like behavior vanished. This demonstrated that the world of quantum mechanics is sensitive not only to physical forces, but also to the structure of information. Physicists who studied this phenomenon realized that ability to maintain superposition depended on a system remaining isolated from outside influences. Any interaction with the environment, whether through stray photons, vibrations, or even thermal motion, could leak information about the system. This leakage destroyed the delicate coherence needed for interference. The absence of interference was not because the particle suddenly changed its nature, but because the conditions required for superposition were no longer present. This insight would eventually grow into the full theory of decoherence, but even before that theory was formalized, the double-slit experiment revealed its core principles. The power of the double slit lies in its simplicity. It presents a clean and unavoidable contradiction between classical expectations and quantum reality. There is no way to explain the interference pattern through classical particles traveling through one slit or the other. There is no hidden force nudging particles into specific regions. The pattern emerges only when both paths remain indistinguishable and the particle retains its wave-like nature. This purity makes the double slit one of the most tested and scrutinized experiments in the history of physics. Every variation, every attempt to explain the pattern without invoking superposition, every proposal for hidden variables has ultimately fallen short. The quantum description remains the only one consistent with all observed data. Experimentalists continued refining their techniques, introducing new tools that allowed them to manipulate and measure quantum systems with unprecedented control. Detectors became more sensitive, barriers were engineered with nanometer precision, and sources of particles were tuned to produce coherent streams of electrons, photons, or molecules. Each refinement confirmed the same principle. Quantum systems do not behave like classical objects. They do not follow a single path or a single outcome. Instead, they evolve according to a wave of possibilities, a wave that must be described using mathematical rules more intricate than anything imagined in classical physics. One of the most striking demonstrations of the power of superposition came when physicists used single photon sources, allowing them to send individual photons through the double slit one after another. Each photon arrived as a lone speck on the detection screen, but slowly, patiently, the interference pattern emerged. At first, a handful of dots appeared in random places, but as the number of photons grew, the structure began to reveal itself. The central bright fringe appeared first, then the secondary fringes on either side. Eventually, the full pattern came into view, identical to the one that classical waves would produce. The photon behaved like a wave passing through both slits, even though it arrived as a single particle. This duality was not a philosophical claim or a metaphor. It was an empirical fact written in the distribution of the dots. The meaning of this behavior is profound. It shows that particles do not have predetermined paths or predetermined properties. Instead, their behavior is shaped by the wave function, a mathematical object that captures the full range of possibilities a system can explore. The double-slit experiment forces us to confront the reality that the universe does not operate according to classical logic at its smallest scales. Instead, it follows the rules encoded in quantum mechanics, rules that allow particles to exist in overlapping states and to interfere with themselves before any measurement collapses their behavior into a single result. From this foundation, the path forward becomes clear. If the double-slit experiment reveals the existence of a wave-guiding particle behavior, then the next question is to understand the nature of that wave. What does the wave function represent? How does it evolve? How can it predict the outcomes of experiments with such extraordinary accuracy? The early pioneers of quantum mechanics confronted these questions as they worked to build a theory capable of describing the strange behavior observed in the laboratory. Their efforts produced the mathematical framework that now forms the backbone of modern physics. As we leave the double-slit experiment behind, its lessons remain with us. It teaches that reality is built from superpositions, that particles do not choose until forced to choose, and that information plays a central role in the unfolding of quantum events. It stands as the clearest window into the true nature of the microscopic world. And as we step forward into the next chapter, we enter the realm where the mathematics of quantum mechanics begins to translate the mysterious behavior of particles into a precise and predictive language. The wave function awaits, carrying within it the answers to how superposition works and why the quantum world behaves as it does. There comes a moment in every scientific revolution when the evidence becomes so overwhelming that the world demands a new language. The double-slit experiment forced physicists to accept that particles behave like waves, yet no one could describe what this wave truly represented. It was not a wave of water or a wave of air or a vibration of any physical medium. It was something deeper, something that lived not in ordinary space, but in the structure of probability itself. To understand how particles could exist in overlapping possibilities, how they could interfere with themselves, and how they could collapse into single outcomes, scientists needed a mathematical tool unlike anything seen before. This tool emerged in the form of PSI, the wavefunction, a strange yet extraordinarily powerful description of the quantum world. When Erwin Schrödinger sought to explain the wave-like nature of matter, he realized that no classical idea could capture what experiments were showing. If an electron behaved like a wave, then its spread across space had to be part of its physical identity rather than a model of ignorance. Psi was born from this realization. It was not a picture of the electron itself, but a description of all the positions the electron could occupy, each weighted by a probability that unfolded smoothly over time. Psi had peaks where the electron was more likely to appear and troughs where it was less likely. It was a mathematical shape that moved and shifted, guided by a rule that allowed it to predict outcomes with astonishing accuracy. To see why PSI became indispensable, one must return to the patterns revealed by the double-slit experiment. The interference fringes were not created by the physical motion of particles, but by the way the wave of possibilities overlapped. Where the possibilities reinforced each other, bright regions emerged. Where they cancelled, dark gaps formed. Psi carried the structure of these possibilities. It was the engine that drove the probability distribution, shaping the behavior of electrons, photons, atoms, and even large molecules. The remarkable thing was that PSI did not describe what would happen every time. It described what could happen in every instance. In that distinction lies one of the most profound differences between classical and quantum physics. When physicists calculated psi for a system, they discovered that it matched experimental results with extraordinary precision. The shapes of atomic orbitals, the positions where electrons would most likely be found around a nucleus, the discrete energy levels of atoms, all emerged directly from applying the Schrödinger rule to PSI. These predictions were not vague suggestions. They were precise structures that matched the spectral lines observed in laboratories around the world. Every time an atom absorbed or emitted light, it did so at energies determined by the form of its wave function. The pattern of the universe, from the brightness of stars to the chemistry of life, depended on the shapes produced by Psi. Yet Psi itself remained deeply mysterious. It was not a physical wave that could be touched or seen. It did not ripple through space the way water does. Instead, it encoded the full range of possible outcomes for a quantum system. When a particle traveled freely, its PSI spread out like a widening cloud, representing the growing number of possible places it could be found. When it encountered a barrier, Psi wrapped around it, producing tunneling effects where particles slipped through regions they had no classical right to enter. When two waves of possibility met, they interfered, producing the same patterns observed on screens in double-slit experiments. Psi was not a metaphor. It was the only structure capable of predicting these behaviors. The strange thing about Psi was that it did not describe a single event. It described the evolution of probability. The particle itself remained elusive until measured. Before measurement, PSI whispered that the particle could be anywhere within its spread. After measurement, the particle appeared in one location, and Psi reshaped itself instantly to reflect this new information. Whether this sudden shift represented a physical change or merely an update to our knowledge became one of the central questions in quantum mechanics. But even without resolving that debate, physicists agreed on one point. Psi worked. It predicted everything from the behavior of electrons in atoms to the outcomes of complex interference patterns. As experiments grew more sophisticated, Psi became even more essential. Spectroscopy revealed that atoms emitted light at specific frequencies determined by the differences between their energy levels, differences that Psi defined precisely. Quantum tunneling, a phenomenon that allowed particles to pass through barriers, was predicted entirely by the shape of PSI near those barriers. Even the stability of matter itself depended on the patterns created by Psi inside atoms and molecules. Without the wave function, electrons would spiral into nuclei, atoms would collapse, and the universe would be unrecognizable. The more scientists relied on PSI, the more they saw that it was the natural language of the quantum world. It describes superposition not as a philosophical idea, but as a direct mathematical statement. A particle in a superposition was represented by a wave function that was a blend of multiple possible states, each contributing to the final pattern of outcomes. Psi allowed these states to coexist until something forced the system to commit to a single result. The wave function did not determine which result would occur in any given trial. Instead, it determined the likelihood of each outcome, shaping the probabilities with exquisite precision. By the time the wave function was fully embraced, physics had crossed a boundary. The universe could no longer be described solely by definite positions and clear trajectories. Instead, it was governed by a deeper, more fluid logic that allowed possibility to play an active role. Psi explained why superposition existed and why interference occurred. It revealed that the quantum world was not chaotic, but structured by a hidden order expressed in the language of waves and probabilities. And yet, one mystery remained. If PSI guided the evolution of a quantum system, what happened when a measurement was made? Why did the wave function seem to collapse into a single outcome? And what physical process caused that collapse? The search for answers would lead to one of the most important developments in modern physics. As physicists explored the meaning of PSI, they found themselves drawn into a realm where familiar ideas about reality no longer held firm. Psi did not describe a single path or a single state. It described a tapestry of possibilities woven together by rules that seemed to belong to a deeper level of nature. This tapestry evolved through time according to the Schrödinger rule, changing shape in a smooth and continuous way. Yet when a measurement was made, the smooth evolution seemed to shatter. Suddenly, the particle appeared in one definite place or one definite state, as though the entire structure of possibilities had collapsed into a single thread. This sudden shift puzzled scientists and sparked long debates about what PSI truly represented. To understand why PSI became so central to quantum theory, one must look at how consistently it matched experimental data. When physicists calculated Psi for the hydrogen atom, they found that the predicted energy levels match the exact spectral lines observed through telescopes and laboratory instruments. When they calculated PSI for electrons trapped in potential wells, they predicted the phenomenon of tunneling, which allowed particles to cross barriers even when they lacked the classical energy to do so. Tunneling was later observed in nuclear decay, chemical reactions, and even in the functioning of electronic devices. Every place where classical physics struggled, SI offered a clear and accurate prediction. The wave function was not merely a mathematical trick, it captured something real, though the nature of that reality remained elusive. Psi spread out over space, and its peaks and valleys determined where a particle was likely to appear. But because Psi evolved smoothly, it allowed particles to drift into regions that seemed classically forbidden. This spreading also explained why interference occurred. When two waves of possibility overlapped, They created regions where the probability of detecting a particle increased, and other regions where it decreased. The resulting patterns were not illusions. They were recorded on screens, counted in detectors, and measured with high precision. As physicists became more comfortable with PSI, they recognized another extraordinary property. Psi existed in a space larger than physical space. For a system with two particles, PSI did not simply describe two positions. It described all possible combinations of their positions, forming a structure far richer than anything classical physics allowed. For systems with many particles, the complexity increased dramatically. The wave function of a molecule with 10 atoms lived in an unimaginable space of possibilities, yet psi still governed its behavior with perfect consistency. This complexity hinted at why quantum systems were so fragile. Any small interaction with the environment could disrupt the delicate structure of PSI, causing the system to behave more classically. This fragility offered clues about the relationship between the microscopic and macroscopic worlds. In the small-scale domain, where systems could be isolated from their surroundings, psi evolved freely. Interference, superposition, and tunneling were all visible. But in the large-scale world, where objects constantly interacted with air molecules, photons, vibrations, and thermal fluctuations, the structure of psi was quickly disrupted. The wave function did not vanish, but it lost coherence. The overlapping possibilities blurred into one another until only classical behavior remained. Although the full explanation of this process would come later with the theory of decoherence, psi already pointed toward the answer. The shape of psi also explained how atoms formed stable structures. If electrons behaved like classical particles orbiting a nucleus, they would continually radiate energy and spiral inward. But PSI revealed that electrons existed in standing wave patterns around the nucleus. These patterns were stable, with each allowed shape corresponding to a specific energy level. This insight transformed chemistry, explaining why atoms bond in certain configurations and why molecules adopt particular shapes. Entire fields of science grew from the understanding that psi controlled the architecture of matter. As scientists explored further, the mathematical structure of psi revealed another remarkable feature. Superposition was not a special case. It was the most natural state for a quantum system. Psi itself was a combination of possible states, each contributing to the overall shape of the wave function. When a particle existed in a superposition, it was not split into parts. Instead, its psi spread across multiple possibilities. Only when a measurement occurred did the system settle into a single outcome. This realization transformed the way physicists thought about reality. Instead of being rigid and fixed, reality at the smallest scales flowed according to the rules of CSI. Yet the apparent collapse of the wave function during measurement remained a puzzle. The Schrödinger rule was smooth, continuous, and reversible, but measurements seemed abrupt and irreversible. This conflict raised one of the most profound questions in physics. Did PSI represent a real physical wave that collapsed when observed? Or was the collapse merely a reflection of new information being gained? Some physicists argued that PSI was a complete description of reality. Others believed it was only a tool for calculating probabilities. But regardless of interpretation, psi correctly predicted every experiment conducted in the quantum realm. This predictive power became the strongest argument for accepting PSI as the core of quantum mechanics. It did not matter whether one believed that the wave function was physically real or merely a mathematical device. What mattered was that it captured the behavior of the universe with extraordinary precision. Every double slit pattern, every atomic spectrum, every tunneling event, every quantum oscillation, all arose from the evolution of psi. Without it, the quantum world would be incomprehensible. As the understanding of psi deepened, scientists prepared to confront the next great challenge. If psi evolved smoothly and continuously, then why did measurements seem to break that evolution? What physical process caused the superposition of possibilities to collapse into a single outcome? The search for this process led to one of the most important ideas in modern physics, a concept that would bridge the gap between the microscopic world of quantum possibilities and the macroscopic world of classical events. That idea was decoherence, and it would fundamentally change the way scientists understood measurement. The more physicists explored the behavior of PSI, the clearer it became that the wave function was not simply an abstract equation, but a living record of possibility itself. Psi was a map of all the ways a quantum system could evolve, a shifting field of potential outcomes shaped by the rules of quantum mechanics. It governed everything from the orbitals of electrons in atoms to the paths particles took in interference experiments. But this understanding brought scientists to the edge of a deeper puzzle. If PSI described all possibilities, then what happened when one specific outcome became real? Why did the universe choose one result when the mathematics allowed many? This question became the heartbeat of quantum mechanics, pulsing through every experiment that involved measurement. When researchers examined the wave function closely, they saw that it flowed smoothly according to the Schrödinger rule. This continuous evolution did not seem to allow sudden jumps or collapses. Yet every measurement resulted in exactly that. Before measurement, PSI contained many possibilities. After measurement, only one remained. The transition was instant and irreversible. No trace of the other possibilities remained in the measured outcome. This strange contrast between smooth evolution and abrupt collapse made physicists wonder whether the collapse was a physical event or simply a shift in knowledge. But even as they debated, experiments continued to confirm that PSI predicted outcomes with unmatched accuracy. One of the clearest ways to see this is through the way atomic structures emerge. The shapes of electron waves around a nucleus are dictated entirely by the form of PSI. These shapes create the periodic table, define chemical bonds, and determine how molecules interact. Without PSI, the stability of matter could not be explained. But PSI also revealed that electrons never occupy a single definite orbit. Instead, they exist in clouds of possibility shaped by standing wave patterns. When an electron is measured, it appears at a single point. But before that moment, its wave function stretches through space in a pattern far more intricate than any classical picture could capture. Psi also explained why particles behaved so strangely in interference experiments. When a particle approaches a barrier with two slits, its size spreads through both openings, forming overlapping waves that interfere with each other. Only when the particle is detected does its position become definite. Before that, its psi describes a world where many paths are available. This view is not speculative. It is supported by every version of the double-slit experiment ever performed. Physicists have sent electrons, photons, atoms, and large molecules through such barriers. Each time, the interference pattern emerges only when the particle remains unmeasured between source and screen. The moment which path information becomes available, even indirectly, the interference vanishes. Psi explains this behavior naturally because measurement selects one branch of the wave function and erases the others from the observable outcome. Yet Psi was not only tied to measurement and interference, its influence extended to countless other quantum effects. Quantum tunneling, for example, occurs because PSI does not disappear at a barrier. Instead, it decreases gradually, allowing a small but non-zero probability for the particle to appear on the other side. This effect explains why the sun shines, because nuclear fusion in stars depends on tunneling. It explains why radioactive particles escape from atomic nuclei. It even plays a role in modern electronics, where tunneling through thin layers is essential for the function of certain devices. Psi draws these possibilities into a single mathematical framework, showing how the universe allows events that classical physics would forbid. As experiments advanced, physicists discovered that PSI could describe systems far more complex than single particles. Entire atoms, molecules, and even small collections of particles could be represented by wave functions that lived in spaces of many dimensions. These multi-particle wave functions revealed that quantum systems could become entangled, sharing states in ways that defied classical separation. Although entanglement would become the focus of its own chapter later, it emerged naturally from the structure of psi. When two particles interacted, their wave functions intertwined, creating a combined psi that could no longer be factored into separate parts. This connection made the behavior of one particle depend on the state of the other, even when separated by large distances. The wave function provided the only consistent way to describe such correlations. Despite its power, psi remained enigmatic. Some physicists believed it represented a real physical wave, existing independently of observation. Others thought it was a mathematical tool for predicting experimental outcomes. Still others argued that the wave function described information rather than physical reality. The debates continued, but the experiments remained clear. No matter how one interpreted psi, the predictions matched observations with extraordinary precision. Reality did not unfold according to classical logic. It followed the patterns encoded within the wave function. By the close of the first few decades of quantum science, physicists accepted psi as the foundation upon which the entire theory rested. But they also knew that something crucial was missing from their understanding. The Schrödinger rule explained how psi evolved until a measurement occurred. But it did not explain how or why measurements seemed to collapse the wave function. It did not reveal what physical process turned overlapping possibilities into a single outcome. This mystery became unavoidable as experiments grew more refined. The answer would begin to emerge decades later, when physicists realized that a quantum system never exists in isolation. It constantly interacts with its environment. These interactions, subtle or strong, blur the structure of psi until only one classical outcome remains visible. This process, known as decoherence, would provide the bridge between the quantum world of possibilities and the classical world of definite events. It would show that collapse was not magic, not philosophy, but a physical process rooted in the way the universe handles information. And so the stage is set. With psi revealed as the mathematical heart of quantum mechanics, the next chapter turns to the question that haunted physicists for generations. What happens during measurement? What causes superposition to fade? What physical mechanism makes the quantum world appear classical? The search for these answers leads into the theory of decoherence, a modern explanation grounded in hard evidence and clear physics. There is a moment in every quantum process when the quiet fluidity of possibility meets the solid certainty of experience. In the world described by psi, a particle can exist in many overlapping states. It can slip through two slits at once, tunnel through barriers, and evolve in smooth waves of probability. Yet the instant we measure it, the spreading cloud of possibilities collapses into a single outcome. The electron appears at one point, the photon takes one path, the atom reveals one energy. The transition feels abrupt, almost violent, as if nature is pulling a thread from a tangled weave and presenting it as the only truth. For decades, scientists struggled to understand what measurement actually meant. Why should observing a system change its behavior? Why should the act of gaining information force the universe to choose? To answer these questions, physicists first had to confront the fact that classical intuition had no place in the quantum domain. In the everyday world, objects have definite positions, whether we observe them or not. A book on a table remains on the table, even if no one looks. A planet orbiting the lowercase sun continues its path regardless of whether a telescope watches it. But the quantum world does not follow this logic. The position of a particle before measurement is not a hidden fact waiting to be discovered. It is a range of possibilities that only becomes definite when an interaction forces the system to settle into one of them. Measurement is not passive. It is an active physical process. This realization led physicists to examine measurement more closely. They began to see that measurement was not a special act performed by a human observer. It was not tied to consciousness or intention. Instead, measurement referred to any interaction that transferred information about a quantum system into a larger, more classical environment. When a particle strikes a detector, when light scatters off an atom, when a system interacts with air molecules or thermal vibrations, information about its state leaks into the surroundings. This leakage breaks the delicate balance required for superposition and causes the system to behave classically. The key was not the human mind, it was the flow of information. The idea that information played a central role in quantum measurement gained momentum as scientists examined the limits of isolation. A quantum system can remain in a superposition only if it is protected from its environment. The moment it interacts with anything larger, the structure of its wave function begins to unravel. The overlapping possibilities, once held together by coherence, start to separate into distinct outcomes. Each outcome leaves a trace in the environment. These traces accumulate rapidly, making it impossible for the system to maintain its quantum identity. What appears as a collapse is actually the environment swallowing the coherence of psi. This understanding opened a new way of viewing the quantum to classical transition. Instead of asking why measurement caused collapse, physicists asked how the environment destroyed quantum coherence. They recognized that every particle in the universe is constantly interacting with countless others. Photons from surrounding light sources bounce off surfaces. Molecules of air vibrate and collide. Thermal energy flows through every object. These interactions are so frequent and so strong at the macroscopic scale that no object larger than a few atoms can remain isolated long enough to maintain quantum coherence. The classical world emerges because the quantum world is never alone. As experiments grew more refined, scientists realized that this picture matched observation perfectly. When particles were shielded from the environment, superposition remained intact. When they were exposed to air, light, heat, or mechanical vibrations, superposition decayed. This decay was not random. It followed clear mathematical rules, indicating that the environment was constantly measuring the system indirectly. Every collision with a photon, every scattering event, every transfer of heat acted like a tiny measurement, nudging the system toward a classical outcome. By the time even a fraction of a second had passed, the coherence of the system had leaked away into the environment, leaving behind only one observable result. This explains why the double slit experiment loses its interference pattern when Witch path information is available. It is not because the particle chooses differently, it is because the environment stores clues about the particle's path. The moment such clues exist, the overlapping waves of possibility cannot interfere. The environment becomes a vast recording surface, keeping track of every interaction. Once enough information has spread outward, the wave function can no longer remain in a superposition of paths. The pattern collapses not by magic, but by physical necessity. The idea that measurement is simply interaction and that collapse is the loss of coherence marked the beginning of a profound shift in quantum physics. It showed that the classical world emerges naturally from the quantum world when systems become entangled with their surroundings. At small scales, isolation can preserve strange behavior. At large scales, interaction washes it away. But even as these ideas took shape, scientists still lacked a clear framework to describe how coherence disappeared. They needed a theory that connected the mathematics of psi with the physical processes that destroyed superposition. This need gave rise to the modern theory of decoherence, a framework that would transform the understanding of measurement from a philosophical puzzle into a scientific explanation grounded in evidence. As the 20th century progressed, the mystery of measurement remained one of the most unsettling puzzles in quantum mechanics. Some physicists argued that the wave function collapsed physically, while others believed the collapse was only a shift in knowledge. But neither view offered a clear physical mechanism. The breakthrough came when scientists began examining not the measurement device itself, but the entire environment surrounding a quantum system. They realized that every interaction, no matter how small, left a trace in the environment. This insight reshaped the understanding of measurement. Instead of thinking of collapse as an abrupt, mysterious event, physicists came to see decoherence as a natural, continuous process grounded in the way quantum systems interact with the world. Decoherence emerged from the work of researchers like H. Dieter Zeh in the early 1970s and Wojciech Zurek in the 1980s. They recognized that quantum systems do not isolate themselves from their surroundings. Particles are constantly bombarded by photons of light, molecules of air, and vibrations from the surfaces around them. Each interaction entangles the system with the environment, spreading information outward. This entanglement destroys the delicate coherence needed for superpositions to survive. The environment becomes a vast sink that absorbs the quantum information, leaving behind only a classical outcome. This process occurs so quickly that it is almost impossible to observe directly at everyday scales. To see decoherence in action, imagine a dust particle floating in a quiet room. At the microscopic level, the dust particle contains countless atoms, each capable of maintaining quantum coherence for an instant. But the dust particle does not float in a vacuum. It is constantly struck by photons from the surrounding light, bumped by air molecules, and warmed by thermal radiation. Each collision reveals information about the particle's position, momentum, or motion. These interactions force the wave function of the dust particle to collapse into a definite state almost immediately. The coherence that would allow the dust to behave like a quantum object vanishes long before any interference pattern could form. The classical world emerges because decoherence works continuously and relentlessly. Experiments confirm these ideas with increasing precision. In quantum optics laboratories, physicists cooled atoms to extremely low temperatures, isolated them from stray photons, and placed them in vacuum chambers where collisions with air molecules were minimized. Under these conditions, atoms retained their quantum coherence long enough to demonstrate interference, entanglement, and superposition. But when even a small amount of heat or light was introduced, the coherence dissipated rapidly. The atoms returned to classical behavior, as though the quantum world had retreated behind a curtain of environmental noise. The experiments showed that decoherence was not a theoretical guess. It was a measurable effect that aligned perfectly with the predictions of quantum mechanics. One of the most striking demonstrations came from ion trap experiments, where individual ions were suspended in electromagnetic fields and cooled to near absolute zero. For brief moments, these ions behaved exactly as quantum theory predicted. They existed in superpositions of positions, oscillated between energy states, and interacted with lasers in ways that produced delicate interference patterns. But when researchers allowed the ions to warm slightly or exposed them to stray electromagnetic fields, the superpositions collapsed. The ions began behaving like classical particles, responding only to definite forces and occupying definite states. The transition was smooth and predictable, matching the mathematical description of decoherence perfectly. Superconducting qubits offered another clear example. These systems used loops of electrical current cooled to extremely low temperatures. When isolated, the current in the loop could flow in two directions simultaneously, creating a superposition of states. But the slightest heat, noise, or electrical disturbance destroyed the coherence. The superposition collapsed into one of the two possible currents. Physicists could predict the rate at which decoherence would occur by measuring the interactions between the qubit and its surroundings. Every experiment reinforced the same message. Superposition was not mysterious. It was simply fragile, easily disrupted by the environment. The clear picture that emerged was that decoherence did not destroy psi. Instead, it spread the information about the system into the environment, making the different components of the wave function inaccessible. The possibilities remained encoded in psi, but they could no longer interfere because the environment carried traces of which possibility had been realized. From the perspective of an observer, only one outcome remained visible, even though the wave function still contained the others in forms that could never again be recovered or recombined. This understanding resolved one of the deepest tensions in quantum mechanics. There was no need for a special collapse rule or a sudden jump in the wave function. The collapse was an illusion created by decoherence. The true evolution of psi remained continuous and smooth, but the environment forced the system into a classical appearance. Decoherence explained why macroscopic objects do not display quantum behavior. It explained why superpositions are visible only under extremely controlled conditions. It explained the disappearance of interference patterns when path information becomes available. It explained the boundary between quantum and classical behavior, without introducing new laws or speculative ideas. Yet even as decoherence brought clarity, it also raised new questions. If superpositions always exist in PSI, but decoherence hides them, then what exactly do we mean by a definite outcome? If the wave function continues evolving, but observers can only see one branch of it, then what determines which branch becomes visible? Decoherence does not answer these philosophical questions fully. It explains how superpositions become unobservable, not why a single outcome is experienced. But for the purpose of understanding the physical process of measurement, decoherence provides the essential framework. It shows that measurement is not a mysterious collapse, but the inevitable loss of coherence due to entanglement with the environment. As physicists embraced decoherence, they realized that superposition was not rare or exceptional. It was the natural state of a quantum system. The classical world appeared only because superpositions decayed so quickly at large scales. This understanding set the stage for what came next. If superposition is the default condition in the quantum world, then the next question becomes far more fundamental. What is the true origin of superposition? Why does the universe allow states to overlap in this way? The answers lie beyond particles and wave functions, in the deeper structure of quantum fields. The rise of decoherence transformed the way physicists understood the quantum to classical boundary. Instead of imagining the wave function collapsing under the weight of observation, they now saw a gradual erosion of quantum coherence caused by countless interactions with the environment. This insight resolved many puzzles, yet it also deepened the mystery in an unexpected way. Decoherence explained why superpositions disappear from view, but it did not eliminate superposition itself. It showed that the quantum world never stops being quantum. It is only hidden beneath the noise and complexity of the macroscopic world. This realization forced scientists to reconsider the very nature of measurement, not as an abrupt event, but as a continuous flow of information shaping what we perceive as reality. With decoherence, the universe appeared in a new light. Every interaction, no matter how subtle, was a form of measurement. A photon bouncing off a particle, a molecule of air colliding with a surface, a whisper of thermal radiation drifting through space, all of these events captured tiny fragments of information. Each fragment nudged the quantum system toward a definite outcome. The environment became a vast recorder, collecting traces of possibilities until only one remained visible. When decoherence acted quickly, the system appeared classical. When it acted slowly, quantum behavior persisted long enough to be observed. This delicate balance revealed why superpositions are easy to destroy, but not easy to erase from theory. They remain hidden in PSI, buried beneath layers of entanglement with the environment. As scientists explored decoherence further, they realized it was not a special process reserved for particular systems. It occurred everywhere, at every scale. Even objects as large as planets or stars had wave functions, but their coherence was destroyed almost instantly by interactions with radiation, dust, and gravitational fields. The universe was filled with decohering, processes that shaped the classical world we see. Yet these same processes also revealed how difficult it is to observe quantum phenomena. To see a superposition, one must isolate a system from the environment completely, shielding it from every possible source of information leakage. This required vacuum chambers, cryogenic temperatures, electromagnetic traps, and extraordinary precision. Whenever such conditions were achieved, superposition emerged as a natural and unmistakable feature of the system. One of the most striking confirmations came from experiments with superconducting qubits. In these systems, electrical currents flowed in loops cooled near absolute zero. Under the right conditions, the current could flow in two directions at once, forming a superposition of states. But as soon as heat or electrical noise entered the system, decoherence destroyed the delicate state. The qubit collapsed into one direction or the other. This behavior matched the predictions of decoherence precisely. The superposition was not lost through a mysterious collapse. It decayed because the environment acquired enough information to prevent the two states from interfering. Larger systems behaved similarly. Optomechanical resonators, tiny mirrors floating on light, could be placed in superpositions of motion, but only for brief moments before environmental interactions erased their coherence. The story repeated across countless experiments, each reinforcing the same conclusion. Decoherence was real, measurable, and unavoidable. This view also helped explain why classical physics works so well at large scales, even though quantum mechanics governs everything. Classical behavior emerges not because quantum rules fail, but because decoherence forces large systems into states that cannot sustain superpositions. The resulting behavior matches classical predictions because the environment continually suppresses quantum interference. The classical world is thus not separate from the quantum world. It is a consequence of it, shaped by the relentless action of decoherence. Yet even with this understanding, one question lingered. If decoherence explains why superpositions become invisible, then what creates superpositions in the first place? Why does the universe allow a system to exist in overlapping states at all? Decoherence tells us why we do not see superpositions in everyday objects, but it does not reveal the origin of the quantum rules that make them possible. To answer that question, physicists had to look beyond wave functions and particles. They had to examine the deeper structure underlying all of quantum mechanics, a structure built not from discrete objects, but from fields that permeate the universe. Quantum field theory emerged as the next great leap in understanding. It revealed that particles were not fundamental. They were excitations in underlying fields that filled all of space. These fields obeyed linear rules, meaning that combinations of different states were always possible. Superposition was not a rare event or a mysterious property. It was an inherent feature of the fields themselves. The wave function described the behavior of these excitations, but the deeper origin of superposition lay in the field equations that governed the universe. Every quantum field could exist in multiple overlapping states, and the particles that arose from these fields inherited this property naturally. Decoherence merely hid it from view, blurring the fine details until the world appeared classical. By the time decoherence had been fully accepted, physicists understood that measurement was not an intrusion upon nature, but a consequence of nature's connectivity. Everything in the universe interacts with everything else, and these interactions shape what outcomes we see. The quantum world is always present, operating beneath the surface, guiding the behavior of matter and energy. But the classical world we experience is a filtered version of that reality, sculpted by the environment's relentless consumption of quantum information. As this chapter comes to its close, the path forward becomes clear. To understand why superposition exists, why particles can inhabit many states at once, and why the universe behaves in such a strange yet precise way, one must turn to quantum fields. These fields form the foundation upon which all particles and interactions are built. They hold the answers to the origins of superposition and the structure of reality itself. And so the journey continues into the domain where particles fade into waves of energy, where space is filled with invisible vibrations, and where the true nature of quantum behavior begins to reveal itself. The deeper physicists pushed into the quantum world, the clearer it became that particles were not the fundamental building blocks of reality. They behaved like waves, they interfered like waves, and their identities shifted depending on the energy and conditions around them. Yet the wave function alone could not explain where these waves came from. It could describe the probabilities, but it could not reveal their true source. To understand the origin of superposition, scientists needed to look beyond particles and even beyond the wave function itself. They needed a framework that described not isolated objects moving through space, but the entire fabric of space filled with dynamic entities. This search led to quantum field theory, a vision of the universe that transformed everything known about matter and energy. In this view, the universe is not made of particles at all. Instead, it is made of fields that stretch across all of space. Each type of particle corresponds to a specific field. There is an electron field, a photon field, a quark field, and many others, each one woven into the structure of the cosmos. Particles are not tiny beads traveling through these fields. They are excitations, ripples that rise out of the fields and pass energy from one place to another. When a particle appears, what truly exists is a local disturbance in the corresponding field. When the particle disappears, the disturbance settles back into the calm background of the field. This perspective may seem abstract, but it has been confirmed by experiment after experiment, revealing a deeper truth about the nature of matter. The most remarkable feature of these fields is that they obey linear rules. This means that if one configuration of the field is possible and another configuration is also possible, then any combination of those configurations is allowed. This is the origin of superposition. It is not a mysterious or rare phenomenon. It is the direct consequence of the linear structure of quantum fields. When two states of a field can exist, they can also exist together. When two vibrations are allowed, the field can support both at once. Superposition becomes not an exception, but the natural condition of the quantum universe. The wave function that describes a particle is simply a way of expressing the state of the underlying field, and the field itself holds the superpositions that shape the behavior of particles. Scientists saw the power of quantum fields in countless experiments, each one confirming the predictions of this deeper framework. One of the earliest clues came from the Lamb shift, a tiny deviation in the energy levels of hydrogen. Classical models could not explain it, but quantum field theory predicted it precisely. This shift arose because the electron field and the photon field interacted in subtle ways, creating fluctuations that altered the energy structure of the atom. These fluctuations were not optional. They were a built-in feature of the fields. They revealed that the vacuum itself was not empty, but filled with restless activity, a background of constant motion at the quantum level. Another remarkable confirmation came from the Casimir effect, where two uncharged metal plates, placed extremely close together, experienced a force pulling them toward each other. Classical physics predicted no such force, but quantum field theory explained it as a consequence of the vacuum fields. The energy of the vacuum between the plates changed because only certain field modes could exist in that confined space. The result was a measurable force that arose from the structure of the quantum fields permeating the vacuum. This effect was small, but it was real, and it provided clear evidence that fields, not particles, formed the foundation of reality. The most precise confirmation of all came from measurements of the electron's magnetic moment. Classical physics offered an approximate value, but quantum field theory predicted a value so precise that it matched experiments to more digits than almost any other measurement in science. This level of agreement was not a coincidence. It showed that the theory captured the true nature of the electron field and its interactions. Each correction to the magnetic moment emerged from the behavior of the field, revealing layers of structure too subtle for classical ideas to grasp. These experiments demonstrated that quantum fields were not abstract mathematical inventions. They were the actual entities that shaped the universe. They filled all of space, interacting, fluctuating, and giving rise to the particles we observe. And because the fields were linear, superpositions followed naturally. A particle moving left and a particle moving right were simply two allowed states of the field, and the field could combine them effortlessly. The wave function expressed these combinations, but the origin lay deeper in the fields themselves. This perspective also explained why quantum behavior did not vanish when scientists studied larger and more complex systems. As long as the system was isolated enough for coherence to survive, the underlying field allowed superpositions to persist. When decoherence removed that isolation, the superpositions faded from view, but the linearity of the fields did not change. The universe still permitted overlapping states, even if the environment made them impossible to observe at large scales. Quantum field theory therefore provided the foundation upon which all modern physics rests. It did not merely describe particles. It revealed the structure of reality in terms of continuous entities that could vibrate, ripple, and combine. And because the rules governing these fields were linear, the universe was free to explore multiple possibilities at once. Superposition was not an anomaly. It was a fundamental property of existence. As scientists embraced this framework, they recognized that superposition extended far beyond individual particles. When multiple particles interacted, their fields became entangled, forming combined states that no longer belonged to any one particle. These entangled states could stretch across great distances, linking the behavior of particles in ways that defied classical expectations. But before exploring those correlations, the next step was to understand how quantum fields create shared states and how superposition expands into networks of interconnected systems. The phenomenon of entanglement awaited, carrying within it the next layer of quantum mystery. The more physicists worked with quantum fields, the more they came to understand that the familiar picture of particles was only a convenient illusion. What appeared as a point-like object was never truly a point. It was the smallest possible ripple in a field that stretched through the entire universe. This ripple could move, spread, and interfere, but it was always part of the larger field from which it arose. The field existed everywhere, even in regions where no particle was present, and because these fields obeyed linear rules, every possible ripple pattern could overlap with every other. Superposition was baked into the mathematics from the beginning. It was not a bonus feature of quantum mechanics, it was the very fabric of the theory. Physicists began exploring how these fields interacted with one another. When two electrons approached each other, they did not exchange tiny billiard ball impacts. Instead, the electron field and the photon field interacted at a deeper level, creating temporary fluctuations that guided the motion of the electrons. These fluctuations were not optional, they were required by the structure of the fields. The ripples of one field influenced the ripples of another, weaving together the interactions that gave rise to forces. Even the simplest exchange between two electrons involved a dance of fields, each vibrating in ways dictated by quantum rules. The richness of this picture became even more striking when scientists examined how fields behaved in empty space. The vacuum, once thought to be nothingness, turned out to be a storm of activity. The fields never rested completely. They flickered with tiny fluctuations, producing pairs of excitations that appeared and vanished too quickly to be observed directly. These vacuum fluctuations influenced the behavior of real particles, shifting their energy levels and altering their interactions. The Lamb shift and the Casimir effect were among the first clear signs of this restless background, showing that the vacuum was not empty, but alive with quantum motion. This constant motion revealed something profound. Superposition did not only occur in particles, it occurred in the fields themselves. The vacuum was a superposition of all possible low-energy configurations, layered together in a subtle balance. When a particle appeared, it was simply a disturbance riding on top of these background fluctuations. And when that disturbance moved through space, its motion was guided by the structure of the field, which held countless possible configurations at every moment. This view made the quantum world feel less like a collection of mysterious behaviors and more like a vast ocean with waves traveling through it. But even in this ocean, interactions were not simple. When two fields interacted, their superpositions could merge. The possible states of one field could become linked with the possible states of another. This phenomenon, known as entanglement, would become one of the most surprising features of quantum physics. Yet it arose naturally from the structure of the fields. When one excitation in a field interacted with another, Their wave functions no longer remained separate. They combined into a single structure that described both at once. The possibilities of one became tied to the possibilities of the other. The universe revealed itself not as a collection of isolated things, but as an interconnected web of fields capable of sharing state information across vast distances. Quantum field theory also explained why superpositions persisted even when particles were not in motion. A particle at rest still corresponded to a ripple in the field, and that ripple could exist in multiple configurations simultaneously. A particle could be in two energy states at once, two spin states at once, or two spatial regions at once. The field allowed these states to coexist as long as nothing extracted information about them. Decoherence was the only enemy of these superpositions, erasing them when the environment gained knowledge of the system. But the fields themselves never stopped supporting superposition, regardless of how quickly decoherence acted. One of the most compelling demonstrations of the field structure came from experiments involving the vacuum itself. Physicists created cavities in which certain vibrations of the field were suppressed. When they placed atoms inside these cavities, the atoms behaved differently than expected. Their energy levels shifted because the available field modes were altered. This showed that the properties of the vacuum were not merely theoretical. They could be shaped and manipulated, affecting the behavior of particles within them. The fields were real, measurable, and essential to understanding the universe. Linear superposition played a central role in every one of these experiments. When an atom absorbed or emitted a photon, the process was described as a transition between field excitations. These transitions depended on the linear combination of possible field states. The atom could be in a superposition of energy levels because the field allowed it. The photon could be in a superposition of paths because the field supported that configuration. Even the vacuum could exist in a superposition of modes. The mathematics left no wiggle room. Superposition was an unavoidable consequence of the way the universe was built. This deeper understanding also reshaped how physicists saw the limits of classical intuition. A particle traveling in two directions simultaneously was no longer a paradox. It was simply a ripple pattern in a field that supported multiple waveforms. A particle appearing to interfere with itself was no longer a mystery. It was the natural behavior of an excitation in a linear field. The universe had always been quantum. Classical behavior was merely the appearance created when decoherence washed away the interference patterns that revealed the finer structure beneath. As quantum field theory matured, its predictions grew more precise. Particle accelerators tested its equations to extraordinary accuracy, confirming that the fields described every known interaction. At the same time, experiments with cold atoms, trapped ions, and superconducting circuits showed that superposition and entanglement were not exotic or rare. They were the default conditions for quantum systems isolated from the environment. In every case, the underlying reason was the same. The fields were linear, and their states could combine without limit. This understanding set the stage for the next great leap. If superposition arose naturally from the structure of the fields, and if entanglement was simply the joining of superpositions between interacting systems, then the universe held a deeper level of connection than classical physics ever imagined. Particles could share information across distance. Systems could remain linked even after separation. And the rules of quantum mechanics would reveal these connections in ways that challenged every intuition. With the foundation of quantum fields now established, the journey continues toward one of the most surprising and experimentally verified features of the quantum world. The next chapter steps into the realm of entanglement, where superpositions are not confined to single systems, but stretch across pairs, groups, and even networks of particles. The world of quantum correlations awaits, carrying within it the next layer of quantum mystery. As quantum field theory matured into the central framework of modern physics, its implications for superposition became impossible to ignore. Every ripple in every field could exist in multiple configurations at once. Every disturbance could unfold as a blend of possibilities. The universe did not need permission to explore overlapping states. It was built to do so. But this deeper understanding also revealed something even more remarkable. The fields that filled space were not isolated. They interacted relentlessly, exchanging energy, sharing information, and blending their states. Superposition was not confined within the boundaries of single excitations. It extended outward, weaving connections among particles in ways that defied classical intuition. One of the clearest examples of this occurred in processes where particles were created or destroyed. In classical thought, particles were immutable, units, born with fixed identities. But quantum fields treated creation and annihilation as natural events. An energetic fluctuation could produce a pair of excitations in a field, and a corresponding process could absorb them back into the vacuum. These transformations showed that what mattered was not the particle itself, but the structure of the field that produced it. And because the field was linear, the states of the produced particles could form superpositions from the moment they existed. Their properties were tied directly to the pattern of field vibrations that gave birth to them. This perspective reshaped the understanding of interactions. When two particles scattered off each other, the event was not simply a collision. It was a moment when their underlying fields exchanged information, altering the structure of their combined wave function. During this process, the superpositions in one field could become entangled with the superpositions in another. The result was a joint state that could not be separated into independent parts. The behavior of one particle became linked to the behavior of the other, not through classical forces, but through the shared structure of their combined field state. At first glance, this seemed impossible. How could two particles remain connected after moving far apart? But the wave function that described them was not a physical thread stretching through space. It was a mathematical expression of their shared history in the field. The entanglement was not a signal passing between them. It was the natural consequence of their joint representation within PSI. Once their states were combined, the field treated them as a single entity with multiple possible outcomes. Distance did not undo this connection because the wave function did not live in ordinary space. It lived in a space of possibilities shaped by the fields themselves. These insights became clearer as physicists studied the vacuum more deeply. The vacuum was not a calm, empty sea. It was a swirling background of fluctuations, filled with virtual excitations flickering in and out of existence. These fluctuations could influence real particles, shifting their energy levels and altering their interactions. But they also created subtle connections between distant points, a faint echo of the field's ability to maintain correlations across space. Quantum fields were not local in the classical sense. Their excitations could stretch over regions much larger than the particles that emerged from them. This behavior hinted at why entanglement arose so naturally. The fields themselves carried the capacity for shared states across distance. As experiments probed these ideas, the evidence mounted. In cavity quantum electrodynamics, atoms placed inside specially designed cavities interacted with modified field modes. These interactions produced entangled states between atoms and photons, showing that the fields could mediate quantum correlations with precision. In superconducting circuits, qubits were linked through microwave fields, creating entangled states that persisted long enough to perform complex operations. In atomic systems, lasers manipulated the internal states of ions, entangling them through shared vibrational modes. Each of these results aligned perfectly with the predictions of quantum field theory. The fields allowed superpositions to combine, and these combinations gave rise to entanglement. Quantum field theory also clarified why superpositions in macroscopic systems were so difficult to maintain. As objects grew larger, their interactions with the environment increased. Their fields became tangled with the countless fluctuations around them. Decoherence acted quickly, tearing apart the delicate structures of superposition and leaving behind only classical behavior. But even as decoherence erased observable quantum effects, the fields underneath remained linear, still capable of supporting overlapping states in principle. The classical world was not a separate domain, but a surface appearance created by the overwhelming influence of the environment. This realization helped unify the understanding of quantum mechanics. Superposition arose from the linearity of the fields. Decoherence explained why superposition faded from view at large scales. And entanglement emerged naturally when the fields of different excitations interacted. The pieces of the puzzle began to align, revealing a coherent picture of how the universe handled information, probability, and connection. These insights also offered a new perspective on the meaning of particles. Instead of being fundamental entities, particles became transient manifestations of deeper structures. Their identities came from the fields they excited. Their interactions came from the ways fields influenced one another. Their superpositions came from the linearity of the field equations, and their entanglement came from the shared patterns of their combined states. Quantum field theory did not diminish the mystery of the quantum world. It deepened it, revealing that reality was woven from vast networks of interconnected fields shaped by rules more subtle than any classical description. As this chapter draws to a close, the path forward becomes clear. With the fields understood as the foundation of superposition, the next step is to explore how these superpositions extend beyond individual excitations and into shared states between particles. The phenomenon of entanglement awaits, a realm where particles communicate not through forces, but through a shared structure of possibilities. And as the next chapter unfolds, the true power of superposition becomes apparent, revealing connections that reach across space and challenge the deepest assumptions about the nature of reality. Long before entanglement was observed in experiments, it lived as a peculiar prediction hidden within the mathematics of quantum mechanics. It appeared as a quiet implication of how wave functions combine when two systems interact. At first, it seemed abstract, a strange suggestion that two particles could share a single quantum state, even when separated by great distances. But as the 20th century unfolded, evidence began to rise around this idea, shaping it into one of the most startling and fundamental features of the quantum world. Entanglement was not a story about communication or force. It was a story about correlation, a story about how the universe encodes relationships in ways that classical reasoning could never anticipate. To understand its meaning, one must watch how it emerges, how it survives, and how it reveals itself through experiments of extraordinary subtlety. The idea first took shape when physicists realized that superposition could extend across multiple systems, binding their fates within a shared wave function. When two particles interacted, their individual possibilities did not remain separate. Their wave functions merged into a single structure that contained every possible outcome of their combined behavior. After the interaction, even when the particles drifted apart, that shared structure remained. If one particle was measured, the other particle's state became determined not by communication or force, but by the correlations built into the wave function. This was the essence of entanglement, a pattern of connection arising from the mathematics of superposition. For many years, this connection remained unsettling, even suspect. Some argued that hidden classical variables must determine the outcomes ahead of time, making the correlations seem mysterious when in fact they were predetermined. Others suggested that quantum mechanics was incomplete, that something deeper had yet to be discovered. But the universe answered these doubts not with debate, but with evidence. In the 1960s, John Bell derived a mathematical inequality that drew a line between the predictions of quantum mechanics and those of any classical hidden variable theory. If hidden variables defined the outcomes, the correlations between particles would obey Bell's limits. If quantum mechanics was correct, the correlations would break these limits. Experiments began in the decades that followed, each more precise than the last. Researchers prepared entangled photon pairs and measured their polarizations at different orientations. Every time they performed the tests, the results violated Bell's limits, matching the predictions of quantum mechanics. These violations did not weaken as experiments improved. Instead, they grew ever clearer. Entanglement was not a statistical fluke or an artifact of measurement. It was a real feature of nature. As technology advanced, the tests moved into new regimes. Entangled photons traveled through optical, fibers stretching across laboratories, then across cities, and finally between ground stations and satellites orbiting Earth. In each case, the correlations persisted. Even when detectors were separated by distances large enough to forbid any signal traveling between them within the time frame of measurement, the outcomes remained aligned in ways only quantum mechanics could explain. Other experiments used ions, electrons, and even cold atoms held in optical traps. Some closed the detection loophole by capturing nearly every particle. Others closed the locality loophole by ensuring that measurement choices occurred so quickly that no influence could pass between detectors. In 2015, teams in Delft, Boulder, and Vienna performed experiments that closed these loopholes simultaneously. The verdict was definitive. Entanglement existed exactly as quantum mechanics described it. As understanding deepened, entanglement revealed itself not as an exotic exception, but as a natural consequence of the wave function structure. It appeared whenever quantum systems interacted and avoided decoherence long enough to preserve their shared state. Once entangled, the systems behaved as parts of a single whole, even when separated by vast distances. But this did not violate relativity. No signal passed between the particles. The outcomes reflected correlations encoded in the wave function from the start. Entanglement was not communication. It was connection. Laboratories then began using entanglement as a tool rather than simply observing it. In ion traps, sets of ions were entangled to perform logic operations for quantum algorithms. Their internal states acted in unison, guided by lasers that shaped superpositions with exquisite control. In superconducting circuits, microwave photons mediated entanglement between qubits formed from macroscopic currents, allowing processors to execute gate operations built entirely upon quantum correlations. Neutral atom arrays stretched entanglement across hundreds of atoms arranged in geometric grids, revealing multipartite structures far richer than any simple pairwise connection. These were not conceptual demonstrations. They were operational machines built on the foundations of entanglement. One of the most fascinating demonstrations came from quantum teleportation, a protocol that used entanglement to transfer the state of one particle to another without moving the particle itself. The process required an entangled pair, a measurement on one particle combined with the unknown state, and classical communication to deliver the final instruction. Teleportation did not transmit matter. It transmitted quantum information, using the structure of the entangled state to rebuild the original state at a distant location. No faster than light signaling occurred. The protocol obeyed all physical limits, while demonstrating the extraordinary utility of entanglement. Over the years, teleportation has been performed with photons, ions, atomic ensembles, and superconducting qubits, each experiment confirming the same principle. Entanglement also revealed itself in the behavior of materials. In superconductors, electrons formed pairs that spread across the entire material in a single collective quantum state. The resistance-free flow of current emerged from entangled correlations within the electron population. In topological materials, edge states reflected global quantum properties that depended on the coherence and entanglement of the underlying system. In cold atom lattices, researchers created entangled many-body states that exhibited behaviors impossible for systems lacking coherence. Everywhere physicists looked, entanglement appeared as the organizing principle behind quantum phenomena. But just as superposition faced decoherence, so did entanglement. The moment information leaked into the environment, the shared correlations weakened. A stray photon, a collision with a gas molecule, or a fluctuation in the electromagnetic field could break the delicate structure that linked the systems. Entanglement was not fragile because the theory was weak. It was fragile because the environment had countless ways to absorb information. The same process that pushed superposition into invisibility at macroscopic scales also pulled entanglement apart when isolation faltered. Yet even this fragility revealed insight. It showed that entanglement was not magic. It was physics, unfolding according to rules that governed every interaction. The rise of quantum engineering transformed entanglement from a theoretical oddity into a practical resource. Quantum computers used entanglement to create states that explored many possibilities in structured ways. Quantum communication networks relied on entangled pairs to distribute keys with security guaranteed by the laws of physics. Quantum sensors used entangled states to detect minute changes with unprecedented sensitivity. In each application, entanglement's meaning remained the same. It was the extension of superposition across multiple systems, a global quantum structure capable of correlations no classical system could reproduce. As Chapter 6 draws to a close, its message becomes unmistakable. Entanglement is not a mystery to be solved, but a feature to be understood. It arises naturally from the linearity of quantum mechanics. It survives as long as coherence survives. It collapses when the environment absorbs too much information. It reveals a universe in which connection transcends distance, not through communication, but through structure. And it prepares the way for the next chapter, where engineered superposition becomes the foundation of technologies that push the quantum world into human hands. For generations, superposition lived in the realm of theory and delicate laboratory demonstrations, a phenomenon glimpsed only when nature cooperated and conditions were perfect. The idea that humans might one day harness this fragile quantum feature seemed almost impossible. A particle following two paths at once, an atom occupying overlapping states, a system holding multiple possibilities until interaction forced a decision. These were behaviors that classical machines could not imitate. And yet, as the 20th century drew to a close and the 21st began to unfold, scientists learned that the boundaries of quantum behavior were not fixed by the laws of physics. They were fixed by engineering skill. What once evaporated under the slightest disturbance could now be coaxed, protected, and shaped with extraordinary precision. Superposition, once a delicate hint of nature's strangeness, became the foundation upon which new technologies were built. The earliest breakthroughs came from superconducting circuits cooled to temperatures only a breath above absolute zero. In this frigid environment, electrons moved as pairs called Cooper pairs, gliding without resistance through loops of superconducting material. These loops could carry currents flowing clockwise, counterclockwise, or in a quantum mixture of both directions at once. It was a macroscopic manifestation of superposition, involving trillions of electrons moving in coherent unity. Engineers found that by tuning magnetic fields and applying microwave pulses, they could sculpt these superposed states, hold them steady for precious intervals, and extract information from them before decoherence pulled them back into definiteness. These devices became superconducting qubits, the building blocks of early quantum processors that demonstrated, for the first time, the possibility of engineered superposition on demand. But superconducting circuits were only one path into this new territory. In laboratories where electromagnetic fields were shaped with exquisite precision, physicists trapped individual ions above arrays of electrodes. These ions floated in carefully balanced fields, isolated from their surroundings and cooled until their motion reached the quiet stillness of the quantum ground state. Laser pulses manipulated their internal energy levels, placing them into superpositions that persisted long enough for intricate sequences of quantum operations. When two ions interacted through their shared motion, their superpositions intertwined, creating entangled states that served as the fundamental logic of quantum computation. These trapped ions did not merely display quantum behavior. They embodied it with a stability and control that made them ideal testbeds for exploring the limits of engineered coherence. In another corner of quantum technology, researchers peered into the crystalline lattice of diamond and found tiny defects called nitrogen vacancy centers. These imperfections behaved like artificial atoms, hosting electronic states that could be manipulated with microwaves and light. What made them remarkable was their resilience. They could maintain superposition even at room temperature, surviving in environments too warm for most quantum systems. Though their coherence times were shorter than those of deeply cooled ions, their robustness made them valuable tools for sensing magnetic fields, detecting minute variations in nearby spin states, and serving as quantum memory in emerging communication networks. With each experiment, nitrogen vacancy systems revealed that superposition was not confined to ultra-cold laboratories. It could survive in the real world with the right protective structure. Other technologies expanded the frontier further. Neutral atom arrays arrange cold atoms into geometric patterns using finely tuned laser beams, allowing researchers to generate superpositions across hundreds of identical qubits suspended in optical traps. Photonic systems harness the quantum behavior of light itself, splitting photons into superposed paths and recombining them to form intricate interference patterns. These photonic qubits traveled through optical fibers with minimal loss, making them ideal candidates for quantum communication. Even mechanical resonators, once thought too massive for coherent control, entered superposition when cooled near absolute zero and coupled to electromagnetic fields. These resonators held overlapping vibrational states, their motion suspended between possibilities that classical intuition would never allow. Yet every one of these platforms faced the same relentless threat. Decoherence loomed over every experiment, ready to erase superposition the moment information leaked into the environment. Vibrations, stray photons, fluctuating charges, and even cosmic radiation could collapse a carefully prepared quantum state in an instant. To overcome this, engineers surrounded their devices with shields, isolated them from thermal noise, refined materials to near perfection, and invented new techniques to preserve coherence. Dynamical decoupling sequences refreshed quantum states faster than decoherence could degrade them. Quantum error correction distributed information across multiple qubits in patterns that allowed errors to be detected and repaired without destroying superposition. Each innovation pushed the boundary of what was technologically possible. As these systems grew in complexity, they revealed another essential truth. Superposition was not simply a feature to be observed, it was a resource to be shaped. Quantum computers required vast networks of qubits holding superposed states long enough to perform operations that classical machines could not match. Quantum communication systems needed entangled superpositions that could survive transmission across long distances. Quantum sensors required coherence so delicate that the slightest disturbance left a measurable trace. In that, every application, the strength of the technology depended on the strength of superposition. Without it, quantum devices offered nothing that classical machines could not already do. With it, they opened possibilities that had never existed in the history of engineering. The pursuit of engineered superposition also illuminated the limits of control. No matter how advanced the shielding or how precise the lasers, the environment could not be fully excluded. Decoherence would always be present, always waiting, always threatening to undo the work of preparation. But rather than defeat, this challenge offered insight. It revealed that the boundary between the quantum and classical worlds is not rigid. It is shaped by the flow of information. The more isolated a system becomes, the longer superposition survives. The more intensely it interacts with its surroundings, the faster coherence dies. In this balance, scientists saw the foundation of a universal principle. Superposition is not prevented by scale. It is prevented by entanglement with the environment. Engineering quantum systems became the art of limiting that entanglement, preserving coherence long enough to extract the benefits the quantum world offers. With each passing year, the progress grew more remarkable. Coherence times improved. Error rates shrank. Quantum processors expanded from a handful of qubits to dozens and then hundreds. Ion trap machines executed algorithms with precision unthinkable in earlier eras. Photonic networks transmitted entanglement across cities. Superconducting processors approached the threshold of error-corrected operation. Neutral atom arrays demonstrated patterns of control that rivaled any classical device. All of these achievements trace their origin to the same phenomenon: the deliberate creation and protection of superposition. As quantum engineering matured, it revealed that superposition was not an abstract curiosity. It was a fundamental part of reality that humans could learn to shape, protect, and utilize. The technologies built from it stood not only as tools for computation and communication, but as demonstrations of the deep structure of nature. They showed that the boundary between the quantum and classical worlds was not imposed by the laws of physics, but by the reach of decoherence. They showed that superposition persisted wherever coherence survived. And they showed that with careful engineering, coherence could survive long enough to change the world. This chapter closes at the edge of a vast frontier. Ahead lie the experimental boundaries of superposition, where scientists push quantum behavior into systems once deemed too large, too complex, or too entangled with their surroundings to ever display coherence. The next chapter steps into that frontier, exploring the limits of quantum control and revealing how far the reach of superposition truly extends into the macroscopic world. From the moment physicists first glimpsed the strange behavior of electrons and photons in early experiments, the question lingered quietly in the background: how far could superposition stretch? For decades, the quantum world appeared confined to the smallest scales, a place where atoms and subatomic particles danced through overlapping possibilities, while the larger world remained solid, definite, and predictable. But as experimental techniques evolved, researchers dared to ask whether the quantum rules truly ended where classical intuition began. The deeper they pushed into this frontier, the more clearly they discovered that the boundary between quantum and classical behavior was not drawn by size or weight or shape, but by the reach of decoherence. Superposition did not end at the microscopic. It ended where the environment overwhelmed coherence so quickly that interference could no longer form. The earliest hints that superposition could extend far beyond individual particles came from experiments with molecules. In the final years of the 20th century, researchers turned to fullerene molecules, structures made of dozens of carbon atoms bound into spherical cages. These molecules were vast compared to electrons, with internal vibrations, rotations, and countless degrees of freedom. Classical reasoning insisted that such complex molecules should behave like miniature billiard balls, too intricate and too lively to sustain coherent wave behavior. Yet when these fullerenes passed through carefully designed interferometers, they produced unmistakable interference patterns. Each molecule behaved as a single coherent quantum wave. Even with thousands of internal motions unfolding within them, they traveled through space in states that explored multiple paths at once. This result astonished the scientific community, revealing that quantum behavior did not stop at atoms. It extended deep into the realm of chemistry and molecular structure. In the decades that followed, experimentalists pushed the limits further, preparing ever larger and more complex molecules for interference tests. Organic compounds containing hundreds of atoms created fringes that confirmed their superposed states. Later experiments reached into the realm of molecules with thousands of atoms, each carrying an internal architecture far more intricate than anything tested before. These molecules were cooled, shielded, and guided through vacuum chambers, so that no stray collision or photon would destroy their coherence. When the interference fringes appeared on detector screens, they revealed the same message every time. Superposition endured until decoherence intervened. Complexity alone did not destroy it. The environment did. The next frontier emerged from the world of mechanical resonators. These devices were engineered from materials such as silicon or superconducting metals, carved into microscopic beams or vibrating membranes. Though tiny by ordinary standards, they were enormous compared to the particles that had once defined quantum behavior. Each contained billions of atoms arranged in precise structures. Yet when cooled near absolute zero, and isolated from thermal noise, these resonators could be coaxed into their quantum ground states. Through interactions with carefully controlled electromagnetic fields, researchers placed them into superpositions of motion. For brief moments, these mechanical objects existed not in a single vibrational state, but in overlapping possibilities, oscillating and not oscillating at once. Even though the coherence lasted only fleetingly, its existence proved that the quantum world could reach into systems large enough to be seen under a microscope. The experiments did not stop there. Superconducting circuits had already shown that macroscopic currents involving trillions of electrons could occupy superposed states. These circuits existed within loops no larger than a grain of sand, yet they behaved as unified quantum objects. The current through a superconducting loop could flow clockwise, counterclockwise, or in a superposed blend of both, revealing interference patterns that depended on magnetic flux threading the loop. In these moments, the quantum world stepped into the macroscopic domain, showing that even collective variables could remain coherent when shielded from environmental noise. These circuits became the basis for some of the most advanced quantum processors in the world, proving that superposition was not a fragile curiosity, but a powerful physical resource. As experiments advanced, scientists began to explore whether spatial superposition could be created in larger systems, not just in internal states or collective motions. The goal was simple in concept, but extraordinarily difficult in practice. Could a physical object containing billions or trillions of atoms be placed in a state where it occupied two distinct locations at once? To approach this question, researchers developed techniques to levitate nanoparticles in magnetic or optical traps. By suspending these particles without physical contact, they removed one of the major sources of decoherence. Cooling them close to their motional ground states reduced thermal agitation. Shielding them from stray photons and gas molecules increased the precious coherence time. Though full spatial superposition has not yet been recorded on this scale, experiments continue to push the boundary closer, revealing that the obstacles are technical rather than fundamental. Alongside these advances, scientists also investigated whether gravity plays any role in limiting superposition. Some hypotheses propose that gravitational interaction might generate its own form of decoherence for massive objects, forcing them into definite states independent of environmental influence. Yet no experiment has confirmed this. All verified data point toward ordinary environmental decoherence as the dominant factor. Whether gravity hides any undiscovered effect remains an open question for future generations of physicists, but the current evidence shows that superposition survives as long as coherence is protected and information does not leak into the environment. The core insight from all these efforts is that the classical world emerges not because superposition stops being possible, but because decoherence acts with overwhelming efficiency at larger scales. A grain of dust in ordinary air undergoes countless collisions with gas molecules every fraction of a second. Each collision carries away information about the dust's position, destroying coherence long before interference could form. Thermal photons radiate energy outward from every warm object, scattering information into the environment at the speed of light. The environment continually measures every macroscopic system without the need for instruments or observers. This relentless flow of information hides the quantum world beneath the classical, not by destroying it, but by drowning it in interactions too vast to reverse. Thus, the boundary of superposition is not a wall, but a slope. At the smallest scales, coherence survives long enough to create measurable interference. At intermediate scales, coherence exists but fades quickly unless isolated with extraordinary care. At macroscopic scales, coherence collapses almost instantly under the weight of countless environmental interactions. The universe never stops following quantum rules. Humans simply cannot access quantum behavior in systems where decoherence overwhelms superposition faster than any experiment can be performed. Yet the progress made so far reveals something extraordinary. Superposition is universal. It reaches into systems far larger and more complex than anyone once imagined. It survives wherever coherence can be protected. It applies to particles, molecules, mechanical resonators, superconducting loops, and engineered quantum devices. And it continues to expand outward as new generations of experiments refine the art of isolation. As this chapter comes to its end, the next step becomes clear. To truly understand superposition, one must also understand what it does not imply. The quantum world is strange, but not magical, counterintuitive, but not contradictory, surprising, but not mystical. The following chapter confronts the misconceptions that surround superposition, clearing away illusions so that the genuine meaning of the quantum world can rise unclouded. Superposition has always carried an aura of mystery, not because its rules are unclear, but because its behavior stands so far outside everyday experience. When people first hear that a particle can occupy multiple possibilities at once, imagination leaps to images of objects duplicated, realities layered, and choices suspended in some ethereal limbo. Yet the more carefully one examines the physics, the more clearly these interpretations fall away. The true meaning of superposition is precise, mathematical, and deeply grounded in experiment. To understand it well, one must first understand what it does not describe, for the shadows cast by misunderstanding can obscure the clarity that quantum mechanics brings. The most widespread misconception imagines superposition as a literal duplication of physical objects. The picture often painted is that of a particle sitting in two places, in the same way a stone might be placed on two different shelves. But this is not what superposition describes. A particle in superposition is not split into pieces. It is not smeared across classical space. Instead, its wave function contains multiple possibilities, each representing a potential outcome with its own amplitude and phase. Before measurement, these possibilities coexist not as classical states, but as components of a quantum state. The particle is not here or there. It is not half in one place and half in another. It is in a condition where classical location does not yet apply. Only when the environment interacts with the system does a definite position emerge. A second misconception proposes that consciousness plays some role in selecting the outcome of a superposed state, as if the universe waits for a human mind to focus before choosing a result. But experiments across many decades have shown decisively that consciousness has no effect on quantum behavior. A measurement is defined as an interaction that causes the environment to absorb information about the system. This interaction may come from a detector, a scattering photon, a vibrating molecule, or even a distant thermal field. Decoherence unfolds whether anyone watches or not. The environment is the observer. Consciousness enters the picture only when humans interpret the data. The universe collapses nothing. It simply evolves in ways that spread information through interactions. Another misunderstanding arises when people imagine that superposition implies the existence of multiple visible worlds overlapping in space. In this view, a macroscopic object like a table might be both upright and toppled until someone looks at it. But in practice, macroscopic superpositions are destroyed almost instantly by decoherence. A table interacts with air molecules, photons, vibrations, and countless microscopic influences. Every one of these interactions carries away information, destroying interference long before human senses come into play. The quantum world allows superposition at all scales in principle, but the classical world appears because decoherence acts with such speed that macroscopic superpositions never survive. Classical behavior is not separate from quantum rules. It is the result of quantum rules applied to systems too entangled with their surroundings to display interference. There is also a popular notion that superposition represents a hidden classical variable waiting to be discovered. This idea imagines that the particle secretly follows one path, and humans simply do not know which until they measure. But interference experiments show that no single hidden path can explain the observed patterns. If a particle secretly chose a path, interference would vanish. Yet interference appears consistently and with exact precision, matching the predictions of the wave function. The universe does not hide classical choices behind the veil of probability. It embodies a state where classical choices are not defined until interactions force them to be. Some interpretations of quantum mechanics speak about branching worlds, where every possible outcome continues in some form. But these interpretations, while mathematically consistent, remain philosophical frameworks. They do not represent additional experimental facts. Quantum mechanics does not require humans to believe in multiple classical realities. What experiments confirm is far more modest and far more precise. When decoherence destroys interference, one outcome becomes accessible and the others become inaccessible. This is an effect of information spreading into the environment, not a proliferation of classical worlds that humans can interact with. Another misunderstanding suggests that superposition grants special abilities, allowing information to travel faster than light or enabling communication across vast distances without a signal. But while entangled states display correlations that appear instantaneous, these correlations cannot carry usable information. They reflect the structure of the shared wave function, which encodes relationships between particles established at their creation. When a measurement is made, the outcome reflects this structure, but no message travels between the entangled systems. Relativity remains intact. Superposition bends intuition, but it does not break the rules that govern the universe. Superposition is sometimes invoked to justify mystical or supernatural claims, as if the strangeness of the quantum world opens the door to phenomena beyond scientific explanation. But quantum mechanics rests on experimental rigor, not imagination. Every prediction it makes has been tested and confirmed within the limits of measurement. It does not grant psychic influence, mental projection, or mysterious powers. It does not respond to human intention. It describes the evolution of wave functions under linear equations, the effects of decoherence, and the structure of probability. Mysticism begins where evidence ends, and superposition remains firmly within the realm of evidence. Even within physics, confusion can arise over the meaning of the wave function itself. Some physicists view it as a physical entity. Others treat it as a tool for calculating probabilities. This debate is ongoing and may remain open until a deeper theory emerges, perhaps one that unites quantum mechanics with gravity. But this debate does not affect the practical meaning of superposition. Regardless of interpretation, the wave function predicts interference, energy levels, correlation patterns, and phase relationships with astonishing accuracy. Its ability to describe reality does not depend on philosophical certainty. It depends on empirical consistency, and that consistency is the reason superposition remains at the heart of modern physics. When misunderstandings are removed, superposition becomes clear. It is not an object being in two classical states at once. It is not a magical effect created by human perception. It is not a gateway to alternate visible worlds. It is a mathematical structure that allows quantum systems to evolve through overlapping possibilities. It reflects the linearity of the Schrödinger equation. It manifests in interference patterns, entanglement correlations, and the behavior of quantum devices. It disappears at macroscopic scales only because decoherence acts too quickly to preserve coherence. The clarity gained here prepares the path for the final step. Once superposition is understood for what it is and what it is not, the deeper meaning of this principle emerges with full force. The next chapter gathers the scientific truths laid bare through this entire journey and presents the lasting insight superposition offers into the nature of physical reality. Across more than a century of investigation, superposition has transformed from a puzzling feature of early quantum experiments into one of the most profound insights in all of physics. It has guided scientists through the smallest scales of nature, through the behavior of atoms, molecules, fields, and engineered quantum systems, and through the intricacies of decoherence that link the quantum world to the classical one. By the time all misconceptions are stripped away, what remains is not confusion, but clarity, not mystery, but structure, not speculation, but a principle built on repeated experimental triumphs. To grasp the scientific meaning of superposition, is to glimpse the architecture of reality in its most fundamental form. The first cornerstone of this understanding lies in the linearity of quantum mechanics, a feature encoded directly into the Schrödinger equation. Because the wave function evolves linearly, any combination of valid states is itself a valid state. This is the mathematical origin of superposition, a rule so simple in form, yet so powerful in consequence that it reshapes the entire behavior of matter and energy. In classical physics, a system must occupy one fixed state at any moment in time. In quantum mechanics, a system can occupy a blend of states, each carrying an amplitude and a phase that determine how these possibilities interfere. This blending is not symbolic or metaphorical. It is the direct physical prediction of the equations that govern the quantum world. The second cornerstone is the role of the wave function itself. Whether interpreted as a physical field or as a mathematical tool describing probabilities, its behavior matches experimental results with a precision unmatched by any theory in the history of science. The wave function determines how electrons form orbitals around nuclei, how photons interfere in double-slit experiments, how atoms behave in optical traps, and how superconducting circuits evolve in quantum processes. It describes everything from the stability of matter to the subtle shifts in atomic energy levels that only careful spectroscopy can reveal. Superposition is woven into the structure of PSI, and through that structure, it shapes the observable universe. The third cornerstone is decoherence, the process by which quantum behavior fades into classical behavior when the environment absorbs enough information to destroy interference. Decoherence does not change the underlying equations. It changes which predictions humans can observe. In a perfectly isolated system, superposition leads to interference patterns that reveal its presence clearly. In a system interacting with the environment, those interference patterns are washed away, replaced by a single classical outcome. This transition is not a collapse in the mystical sense. It is the natural consequence of a system becoming entangled with degrees of freedom that spread outward uncontrollably. Decoherence explains why superposition dominates the microscopic world and disappears almost instantly in macroscopic objects. Together, these principles reveal the scientific meaning of superposition. It is not a trick performed by nature. It is not a loophole in classical reasoning. It is not a speculative idea at the edge of science. It is the mathematical expression of possibility itself. In the quantum world, the universe evolves through overlapping outcomes that combine and interfere until interactions freeze a single classical result. Superposition allows the universe to explore the structure of possibility before committing to a visible state. The visible world, shaped by decoherence, records only the classical outcomes. The quantum world, described by superposition, holds the deeper layers of physical reality. This understanding illuminates every corner of modern physics. Quantum computers do not rely on magic or secret paths. They exploit the structure of superposition to shape interference patterns intentionally, guiding computation not by evaluating all possibilities at once, but by arranging them to cancel and reinforce in ways impossible for classical machines. Quantum communication does not bypass the speed of light. It uses superposition and entanglement to create correlations with remarkable properties, all fully consistent with relativity. Quantum sensors do not gain their sensitivity from supernatural sources. They use fragile superpositions of atomic or mechanical states to detect changes far too subtle for classical devices to measure. The scientific meaning of superposition also extends into the realm of quantum field theory, where particles emerge as excitations of underlying fields. In this framework, superposition is not limited to particles occupying multiple states. It describes how fields themselves can exist in combinations of configurations, creating interactions and correlations that match the predictions of experiments with astonishing accuracy. The Lamb shift, the Casimir effect, and the anomalous magnetic moment of the electron all arise from the interplay of superposed field states. These effects confirm that the quantum structure of reality is not abstract. It is tangible and measurable. Yet even with these monumental achievements, the meaning of superposition leaves open questions for future exploration. What is the ontological status of the wave function? Does it represent physical reality or information about reality? How does superposition integrate with gravity, a force whose quantum description remains incomplete? Does the universe itself exist in a vast superposed state before decoherence settles its large-scale structure? These questions lie at the frontier of physics, where quantum mechanics and cosmology meet. But they do not weaken the meaning of superposition as established by experiment. They reveal that the universe is still offering questions to those who observe it closely. Superposition also provides a deeper philosophical insight, one grounded not in speculation, but in scientific practice. It shows that reality is not built from certainty. It is built from structured possibility. Classical outcomes emerge from quantum possibilities only when interaction forces them to do so. Before that moment, systems evolve according to rules that allow overlapping futures, each contributing to the final pattern. This view does not diminish the classical world. It reveals it as a particular expression of a far richer underlying structure. As the journey of this book reaches its final moments, the meaning of superposition stands revealed as both simple and profound. It is simple because it arises from a linear equation and manifests wherever coherence survives. It is profound because it reshapes the way humans understand the universe, replacing determinism with probability, classical objects with quantum possibilities, and static forms with evolving wave functions. Superposition is the quiet engine behind the structure of matter, the foundation of quantum technology, the explanation for interference and entanglement, and the bridge between what the universe could be and what it becomes upon interaction. It is the rule from which the classical world emerges and the principle that guides the future of quantum science. To understand superposition is to recognize that the universe is richer, deeper, and more fascinating than classical experience ever suggested. It is to see that certainty is the exception, not the rule. It is to glimpse the architecture of reality as it truly behaves, measured not by intuition, but by the unerring precision of experiment. And it is to accept that beneath every definite outcome lies a sea of possibilities, woven together by the mathematics of psi, waiting for the moment when interaction narrows them into the single familiar world that humans call reality.